a better discussion, I think. And our next speaker
Thank you.
is Professor I.M. El-Faham.
Good morning, everybody. Yeah, I'm originally from Alexandria University, but currently I'm working at King Saud University. So this work is collaboration between Alexandria University, King Saud University, and South Africa, and Barcelona University. Triazine has three main molecules, which is 1,2,3 or 1,2,4 or 1,3,5. The most useful one and the most common one is the symmetric tyrosine. It has, this one has, I will go quickly for the first part, and I will, because it's time limit. So tyrosine, we consider it as tyrosine, S-tyrosine, very useful in many fields, like first used as a drug and anti-cancer agent for treatment of cancer, breast cancer, ovarian cancer, or colon cancer, colon cancer. And then developed to another derivative according to the reactivity of the substituent on the tyrosine ring. So this is found that the reactivity depends on the type of substituent on tyrosine. So it's used in drug and medicinal chemistry like anti-cancer, anti-Hashimoto drug, anti-tuberculosis, anti-inflammatory, antiviral. It has too many application in drug systems. This is some example for the anti-cancer derivative of tyrosine. This is another for kinase inhibitor. This is one originally published, and to compare the tyrosine, triazine with diazine, found that the triazine is more reactive than diazine. The same, which is this one, the tetrazole is normally used for treatment of antimetabolic activity. Found that the triazine is most reactive. And also, they make some screening on some triazine derivative as anti-cancer by Institute of Cancer. This one also used as anti-cancer derivative. A lot of drugs used. Another application which is used for triazine is the corrosion inhibitor. It has a very good corrosion inhibition for the steel in acidic medium, specifically acid medium, because of the nitrogen, and it has something like a pencil ligand, so it inhibit the corrosion force. Also, it's used in a modification on polyethylene glycol, and use it for synthesis of metal nanoparticle like silver, platinum, carbon, nickel, and we have some project is for the silver nanoparticle. Found that it prevents the the corrosion of steel. Also, it makes a healing, it assists for healing of the cracking of the steel. This is also used also for modification of silica, and it's used for drug system and drug activity, and also used for synthesis of many metal nanoparticles. This is some polymers also used based on triazine core. It's used for as it has very high thermal stability and used as shorting foaming agent. It has very good application for shorting foaming agent. Also used for synthesis of some tendrimers. It's a very huge compound. It's used for drug delivery systems. And this is one example also. And this is actually my field, is a peptide synthesis and amino acids. This is on here. It's used as in situ activation for amino acid for synthesis of the peptide bond in solution and solid phase synthesis. We stop in this one. This is our target. Why? The dimethoxy triazine is used as in situ coupling reagent, while the dimorpholine derivative we cannot use it. So this means that the function group or substituent has a major influence on the chlorine on the tyrosine. So why? Because the chlorine on the tyrosine, it has a different activity. It depends on the substituent on the triazine. The first substitution we can use at 0 degrees. Second substitution room temperature, and the third substitution we have to go to the higher temperatures. It's very easy to synthesize this derivative, symmetric one. It can make a tri-hydroxy or tri-amino or tri-side. But our major field is making like a game. We need to make a different nucleophile, a bit like one oxygen, one nitrogen, and one sulfur. So what is the order of this one? And how we can succeed with this one? So we have to do like a game, playing with the molecules and doing some this substitution. This is our aim project here. We selected this trifunctional group, which is the amino group, which is the amino, it's a major part for the amino acid. Sulfur found that in cysteine amino acid, and the hydroxy found in tyrosine and serine derivative. So we have to go through this one. So we have to put the first amine and thiol derivative and the oxygen, and then make the second substitution. Like a game, that's thiol and then put amine and try to put the alcohol, or thiol, put the alcohol and play with the game. Just play with the game, and then every time we have to separate the product from each one. So we did this actually. We make this reaction actually. So we make the first substitution. We got a very good yield by HPLC, as indicated by HPLC, almost 100% for the first substitution reaction. So for the second, we took the second here, we put thiol and put the amine, nothing had happened. And the same oxygen, if we put the amine and put the oxygen, nothing had happened. So what we have to do is, we took this one, the sulfur, and make the second substitution with the amine, I got almost 100%. But when we tried to put the oxygen in the third substitution, we failed. We didn't get the right product. And the same with the other oxygen. We put the amine, and then we put the sulfur, the third substitution, nothing happened. We can get second substitution, but for the third, we failed to get the right product. Finally, we tried with the oxygen, and then we put the sulfur for the second substitution, we get almost 100% yield. This is the aim, is how to get the 100% yield also. Good quality in moderate temperature. We don't need to go to higher 60 because the amino acid is sensitive to high temperatures. So we try with the finally with the oxygen, and then with sulfur, and with the nitrogen, we succeeded with this one to get a good yield and purity from the product. So the order is first oxygen, and second sulfur, and then the third one is nitrogen. This is experimental work we found. We try to understand what's happened theoretically. We did some calculations. We have a very good student from India. She's doing a calculation to measure the charge on the chlorine atom for the triazine, which is the trichloro, and measures charge for each carbon. We found that the chlorine, it has the same charge for the three because they are symmetric. But once we substituted one, with the first substitution, it depends on the type of first substitution, oxygen, nitrogen, and sulfur. So we found that what here, the amine, and then sulfur, oxygen is almost the same. That means the amine, it reducing the charge on the chlorine, which is decrease the activity. That's why the reaction didn't proceed for quality. And then we still found that for the first substitution, second substitution, we can look into oxygen and sulfur. And we measure the charge on the chlorine atom, found that the chlorine has the highest in this state. So this is agree with the experimental result. So the final conclusion for this reaction is we have to go through the order. If we need to put 3 different nucleophiles, like oxygen, nitrogen, sulfur, or 2 nitrogen and 1 sulfur, so we have to go through the order. We have different nucleophiles, oxygen, nitrogen, sulfur, so we have to substitute first the oxygen, sulfur, and nitrogen, because the oxygen, it activates the substitution for that. But the nitrogen, it deactivates and reduces the charge. If you need to try to make 2 symmetric and 1 different, like oxygen and 2 nitrogen, so we have to go to the nitrogen first, oxygen first, and then we do the second and third substitution for the amine because it's the same. So we have to go through this order. Found that this regard is the order was found to be first alcohol, then thiol, and then finally amine. These results are here expected to be useful in medicinal chemistry because the major reactivity of the triazine derivative, it depends on the type of substitute. It depends on the type of substitute, it depends on the type of inductive effect and resonance effect. We found also for many different drugs that the electron withdrawing group on the triazine derivative increase the activity against the main target disease. So this one will be for drugs designed incorporating the S-triazine core, as well as for the construction of conjugated of 2 or 3 chemical biological enzymes. So finally, we would like to thank you, our friend in South Africa. Yahya Ghali is from Egypt, but he got his PhD from South Africa. This is Animeka Farms doing the theoretical calculation. Ashir Kurama and President Fernando Alvarez, we have been collaborating with us almost over 25 years. And now we have collaborating in this amino acid. We have too many patents, we have many publications with type senses. So I'd like to thank you for attendance and
Thank you.
questions.
Okay,
Sorry. It's too cold.
yeah. It's dripping too.
Question final session?
We'll do questions
Okay.
after, according to the rules that they gave me.
We just-